Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistance, and today we're looking at rate laws. Specifically how to deal with problems wherein you're given a series of experiments and it's asking for information based on those experiments and determining the rate law, the rate constant, and the rate of reaction under specific conditions. We have here our chemical equation right here. And we have our 3 experiments. Okay, and we're going to use that information to give to answer all the questions that are given in this example. So we can write the rate law in very generic terms, specifically that the rate is equal to some constant times the concentration of ammonia to some power, let's call it x, times the concentration of molecular oxygen to some other constant power y. And the key here is trying to, in determining what the rate law actually is to find out what that x and y is, and also to find out what the k is for our rate constant. And then using that information, we can then do our last piece, and by plugging in the concentrations of ammonia and molecular oxygen. So what we're going to do is we're going to look at each of these experiments in pairs. We're going to look at the fact that experiment 1 and experiment 2 has an increase in its concentration of ammonia, but is constant when it comes to its concentration of molecular oxygen. Conversely, experiment 2 and experiment 3 shows an increase in its molecular oxygen concentration, but no increase in its ammonia concentration. You could just as easily choose experiment 1 and 3 and pair those off, and experiment 1 and 2 and pair those off, just as easily as one or the other. Or you can use experiments, just whatever combination of experiments makes sense to you, go ahead and use those. But really what you want is you want one group that's changing and one group that isn't changing. So in this case, it makes the most sense to pair off 1 and 2 and 2 and 3. Okay, so we're going to look at writing our rate law as a ratio. So we're going to say the rate of experiment 2 over the rate of experiment 1. I chose 2 over 1 because if you look at our initial rates, 2 is greater than 1. So it makes the numbers easier to deal with. So rate 1, rate 2. And we're going to just write what the initial rates are. So we have 10 times 10 to the minus 5. We don't worry about the units because it's all going to cancel out, but it's molars per second. And then 2.5 times 10 to the minus 5 is our rate 1. And that is equal, if you do the calculation, it's equal to 4. Sometimes it'll equal a nice round number. Sometimes it'll equal something very close to a round number, and that's due to scientific notation and the truncation at certain points. So you just have to kind of make your best judgment when it comes to that. So we have 4 is the relation between 2 and 1. Given that information, we can then look at our rate equation, which we did over here with the rate is equal to K times the concentration of ammonia to the X power times the concentration of molecular oxygen to the Y power, and we can plug in our values. So for experiment 1, or let's do experiment 2 first. Experiment 2, we would have K times 8.0 times 10 to the minus 3 to some power x times y times 3.0 times 10 to the minus 3 to the y power. And then our ratio, we'd have k times 4.0 times 10 to the minus 3 to the x power, also times 3.0 times 10 to the minus 3 to the y power. This is rate 2 over rate 1, just as it is over here. Okay, so now we can cross things out, right? Both of them have k, so they cancel out. Both of them have this 3.0 times 10 to the minus 3 to the y power, so we can cancel that whole thing out. And we're left with 8 times 10 to the minus 3 to the x power over 4 times 10 to the minus 3 to the x power. Simply put, we can just take that information and say that that's got to equal our 2 times 2 to the x power, which has to equal what we found to be 4 in our previous example over here. Because 8 over 4 is 2, so that gives us our 2, and then to the x power, because you don't get rid of that x. So now we have to figure out what 2 to the x power, at what point does that equal 4? And it's pretty obvious on this point that it's 2, but if you wanted to, you could do properties of logarithms and find that the log base 2 of 4 is equal to x, and then solve it using other properties of logarithms and change a base formula wherein you do log of 4 over log of 2, and that'll give you 2. Or you could just recognize that 2 squared is 4. Either way is equally valid. It's useful to know these properties of logarithms because what if it was 5 instead of 4? Or what if it was 6 instead of 4? 2 to what power equals 6? That's not readily available information unless you are comfortable with decimals. So it is to your benefit to understand how to rewrite in terms of logarithms. So we now know that our x we now know that x is equal to 2. Now we can go back and we can look at, let's clean up some of this. And the only thing we're going to keep is our rate expression. Except we can change this part, this x, took a little too much. We can now change this to a 2. So we're getting closer, right? The next step will be to do the same thing for y. In which case we'd have to look at the concentration of O2 that's changing. And we're going to do that with the relation between rate 3 and rate 2. Because rate 3 and rate 2, the difference between them, oxygen is changing, but ammonia is not. So we're just going to leave it like that. And in that expression, you'll find it's 20.0 times 10 to the minus 5 molars per second over 10.0 times 10 to the minus 5 molars per second, which simply equals 2. Okay. So now we can rewrite our rates. We can say rate 3 over rate 2 is just going to be k times 8.0 times 10 to the minus 3. We know that to be squared times O2 to the y power, and our O2 in this case is 6.0 times 10 to the minus 3. and it's going to be to the y power. And then rate 2 is k times 8.0 times 10 to the minus 3 squared times 3.0 times 10 to the minus 3 to the y power. Well, again, k's cancel out. 8.0 times 10 to the minus 3 squared cancels out. So we're left with 6.0 times 10 to the minus 3 to the y power over 3.0 times 10 to the minus 3 to the y power, which gives us 2 to the y power. Write that down. And that has to be set equal to 2. Again, this one is really obvious. You can do the changes in logarithms, but we know that anything to the first power is going to be itself. Any number to the first power is going to be itself. So in this case, we're going to just do y is equal to 1. So if we were to rewrite our expression, we end up getting, I'm going to erase some of this to make more room. Okay. So we now know that y is to the first power. So that is our rate law. So now we need to find out what our rate constant is. And to do that, all you have to do is pick one experiment. Doesn't matter which one. I'm going to go ahead and choose experiment 1 because it's the first one. The first thing you're going to want to do is solve for k. So we're going to divide everything by the concentration of NH3 squared and O2. NH3 squared O2. That's going to cancel with that, and we're left with K is equal to the rate times NH3 squared times O2 squared. And there it is. Okay, so now we just need to pick an experiment and plug in our values. And again, I said experiment 1, so that's what we're going to do. So our rate is 2.5 times 10 to the minus 5 molars per second. Underneath, we have our concentration of NH3, which in this case is 4.0 times 10 to the minus 3 quantity squared times the concentration of O2, which is 3.0 times 10 to the minus 3. And this is molars and molar. Okay? So once you've done that, you'll find that your K value is approximately 5.2 times 10 to the second power per molar squared per second. And that is our K value. So we can rewrite our rate law yet again, this time using all of our known values. So we have 5.2 times 10 to the second power molar per molar squared per second times NH3 concentration squared times the O2 concentration. So this is our refined rate law, wherein we have our rate constant as well as the appropriate exponents on the concentrations. Now we can look at our last thing that we need to do, which is finding the rate of reaction when the concentration is set to certain values. So all we need to do now, let's use blue on this one, 5.2 times 10 to the second power per meter squared per second times concentration of ammonia that they want to use is 21.0 times 10 to the minus 3 molar squared times 16.0 times 10 to the minus 3 molar. And if you do that out, you'll find that you end up having a unit of molars per second and a value of 3.7 times 10 to the minus 3. And that's all there is to it. It was very long and involved, but it's easily doable. I just took the extra steps to make sure that it was very clear.